Hi, I'm Kurt Akeley. I'm one of the founders of Silicon Graphics, a workstation company that specializes in building machines that implement high-performance 3D graphics. Over the past 10 years, I've been involved with all of the graphics designs at Silicon Graphics, and in particular, I've been responsible for the architecture of the graphics systems in all of our high-end products. Today, I'm going to talk about architectures for hardware systems that implement high-performance interactive 3D graphics. Rather than just describing systems I've built in the past, I'm going to describe alternatives and describe their advantages and disadvantages. Here's an outline for what I'm going to go over in the next hour or so. First, I'll give you some application examples demonstrating what 3D interactive graphics is actually good for. We'll talk a little bit about the kind of 3D graphics that we'll be dealing with today. Then I'll develop an algorithm model, a model for how the graphics we'll be dealing with works. Then we'll go over the computational requirements for that algorithm model. And we'll get to the meat of this thing, which is the actual opportunities to use parallelism in 3D graphics architectures. I'll spend a little bit of time talking about context switching and how it influences those architectures. Finally, I'll mention just briefly some alternative architectures. So we'll have gone over a small subset of possible architectures, and I just want to make sure you all understand that there are a lot of other alternatives out there as well. And finally, I'm going to give you a little bit of my philosophy in the form of some designer's notes. There are many applications for interactive 3D graphics. For example, mechanical designers can manipulate 3D components, gaining both a fuller understanding of their shape and also of their relationships to each other. Vehicle operators can be subjected to realistic environments without risk to themselves or to others, and without the cost of actual in-the-seat experience. Commercial aircraft pilots receive much of their training in simulators with sophisticated 3D image generators. The person who piloted the last commercial flight you were on probably had a full passenger load the first time he or she flew that type of aircraft. Finally, scientists use interactive 3D graphics to view systems in a way that they couldn't otherwise be viewing them. For example, molecules can be viewed, their interactions, the way they fit together in an interactive situation where the scientist makes changes to the equations that are controlling the shape of the molecules and then sees what the results are. Likewise, we can view entire weather systems, a capability that, while possible with the satellite, can't be done with the sort of color and resolution that can be achieved with a graphics system. And of course, who would ever think of manipulating a jello mold extrusion without the aid of 3D graphics? They're awfully good for games, too. Okay, so let me go over a couple of the important concepts, why it is that 3D graphics is so useful. The first thing is 3D interactive graphics allows direct feedback. The person who is manipulating the mouse or turning the knob is able to see immediately what the effect of that operation is on the screen. It turns out that your ability to interact with data is greatly increased if you can have immediate feedback. The second thing is that what we're after here is not generally the generation of realistic images. What we're after is useful images, images that convey information. Now, in some cases, such as flight simulation, in order to convey information effectively, the image has to be fairly realistic. But in a lot of other situations, it's not only not particularly important that it be realistic, but it's often important that the images not be realistic. For example, it's useful to be able to represent stress on a solid model as different colors. It's something that will never happen in real life, but it's a very useful way to be able to envision the way stress is affecting a model. Likewise, it's nice to be able to pass a cutting plane through a model and to be able to see what's inside without doing any physical damage to the model itself. On the other hand, the human visual system is incredibly well adapted, and it is useful in some cases to do things that add realism to the scene to the extent that they allow people viewing the scene to make more sense out of it. For example, complicated three-dimensional shapes are almost impossible to figure out the geometry of without actually having some lighting in the scene. So it's very standard in high-end graphic systems to do lighting calculations. But again, the calculations are done in a way that adds information to the scene. They're typically not done in a way including reflections and shadows and all the rest that just adds realism without adding information. Finally, a machine that renders only one scene at a time is useful. In fact, flight simulators almost always deal with just one scene. However, just as personal computers are moving toward multitasking operating systems, so also of high-performance graphics systems. A significant part of the work in implementing a high-performance graphics system is dedicated to supporting multiple graphics processes, rather than just implementing all the rendering that you've seen in these examples. There are many ways to do 3D interactive graphics. Today we'll talk about graphics based on three simple types of primitives: points, lines, and polygons. Though all three primitives are defined in three-dimensional space, none is actually three-dimensional. Points have 0 dimensions, lines have 1 dimension, polygons have 2 dimensions. There is true three-dimensional data out there. It's available from things like CAT scans and MRI scans and some biological confocal microscopes, for example. This data is very useful, but using that kind of data is not what I'm going to be talking about today. I also won't be talking about dealing with higher level primitives. For example, sometimes complex surfaces are described directly mathematically and rendered directly from that description without being reduced to polygons. We're not going to talk about that case either. Just as 3D graphics can be implemented with different fundamental primitives, it can also be implemented with different display techniques. For example, it is possible, though not usual, to generate true 3D displays. Such displays generate perspective automatically as they are viewed, and can therefore be viewed from more than one position at a time. Or in other words, more than one person can look at it at a time. Today's talk is concerned only with graphic systems that project points, lines, and polygons to a two-dimensional surface. That surface is typically displayed using a cathode ray tube, just like your television or typically the computer you work at. Like a movie, the display tube can be viewed from more than one position, but the perspective is correct for only a single viewing position. The two-dimensional projected image is stored in a Framebuffer, which is an array of memory elements, each storing red, green, and blue intensities. Each element is referred to as a pixel, or a picture element. Framebuffers were unusual 15 years ago because integrated memory density was not great enough for them to be cost-effective. Today, however, the Framebuffer is the standard way for a computer to drive a cathode ray tube, whether the image is generated from two-dimensional data or three-dimensional data. Windows systems such as the X Windows system and Microsoft Windows assume the existence of a Framebuffer, for example. The mathematics of 3D rendering involve defining a reference coordinate system, typically called the world coordinates, and positioning both the primitive points, lines, and polygons and the viewer in this coordinate system. Motion is simulated by regenerating the scene over and over again, moving the primitives or the viewer position as desired. An important thing to keep in mind here, those of you who are familiar with typical two-dimensional systems, is that it typically isn't possible in a three-dimensional system to use one of the images that you've created as a source for another image. So a frequent trick in two-dimensional graphics is to copy a region of the screen to produce a new image on the screen. New in the sense of the organization of the image, but not new in the fundamental values of the pixels. That works in two dimensions because the frame-to-frame differences are frequently just two-dimensional shifts in the scene. In a three-dimensional scene, however, it's almost never the case that one frame and another frame are related in any pixel-to-pixel way. Rather, it's required that each new frame be completely regenerated by reprojecting all the points, lines, and polygons to the Framebuffer. When the image regeneration is done at least 10 times per second, the person viewing the resulting image experiences smooth motion, rather than repeated still images. When the regeneration rate reaches 30 to 60 per second, the resulting motion becomes indistinguishable from real motion. Television in the United States, for example, is broadcast with 30 complete frames per second. While graphics systems designed for two-dimensional rendering typically have only a single frame buffer, three-dimensional systems almost always have two frame buffers. One buffer holds the latest completed image, which is being displayed on the cathode ray tube. The other is used to generate the next image. When the next image is completed, the buffers are switched. This use of two frame buffers is referred to as double buffering. All three primitive types are represented as vertexes. A vertex is simply a position in three-dimensional space. It may also include some attributes, for example, a normal vector that represents the orientation of a hypothetical surface at that position in space, or also possibly red, green, and blue color components that describe the material color at that position in space. In any event, the actual area of the primitive isn't represented. The body of lines, the areas of polygons, are represented only by implication in the primitive database. Okay, so primitives are represented as vertexes. How will we model the conversion of these vertexes to an image in the frame buffer? First off, the vertexes exist in some kind of database, and the database, from the perspective of this talk, is under the control of the application programmer. We're not going to talk about hardware systems, although some do exist where those vertexes are controlled by the hardware system. Instead, we'll work with a model that the vertexes in the database are controlled by the application, and somehow that application just proceeds to deliver this torrent of vertexes to the hardware. Given that, we could choose to treat the vertexes that represent points, lines, and polygons individually. We could build ourselves a block diagram that kind of looked like, okay, here are points, here are lines, here are polygons. We don't choose to do that. It's better in almost all cases to emphasize the sameness of things rather than the difference between things. So rather, we stick with the fact that not only are all primitives basically composed of vertexes, but that after they've been rasterized, after they've been turned to pixels, they're all just pixels. So we'll choose to emphasize in our architecture a section that handles vertexes and handles vertexes the same in all cases, a section that converts vertexes to pixels, and this section has to be different for points, lines, and polygons because the rules for doing those conversions are obviously different for those primitives. And finally, a section that handles all of the operations on pixels, which will again do exactly the same, regardless of whether the pixels came from points, lines, or polygons. So we understand a model for converting primitives into framebuffer images. Why not simply implement this model using a general purpose processor? Why build special purpose hardware? The answer is pretty simple, and I'll cover it in the next few slides. Basically, what it amounts to is the amount of computation it takes to do the kind of image generation you saw in those examples at the kind of frame rates you saw in those examples is extraordinarily high. For example, if we just consider a simple case, somewhat like the flight simulator demo, a scene with about 17,000 vertexes in it being rendered into a frame buffer with 1280 by 1000 pixels, or about 1.3 million pixels. Let's talk first about the amount of computation it takes to transform vertexes in that scene. Turns out about 24 floating point operations to transform the position of the vertex, another 28 to transform the normal that described the surface direction at that vertex, another 28 to do a very simple lighting calculation, 6 more simple tests to make sure that the vertex is indeed in the viewable volume of the scene, and finally 17 operations to project the vertex from its three-dimensional coordinate system to the two-dimensional system of the screen, for a total of on the order of 100 floating point operations. Now this is kind of the bottom of the barrel. You can't do much better than this. It's real easy to do worse. For example, if you do more complicated lighting, take account in your lighting how far the light is from the objects, add more lights to the scene, add objects to block the light so that shadows are introduced. If you add clipping planes, in addition to the planes that describe the basic viewing volume, if you in fact have to do some clipping. So all we've talked about so far is checking to make sure the vertexes are in. If they're not in, and especially in the case of triangles, there's a significant amount of work to be done. Finally, if you're going to attempt to map images onto these polygons, something that is referred to as texture mapping, it is very easy to add up a count of 200 floating point operations, and without pushing very hard, we could do 300, 400, or 500. So given our model here of 17,000 vertexes per scene and drawing that scene 60 times per second, that works out conveniently to 1 million vertexes per second. So take whatever number of floating point operations it requires to deal with one vertex, multiply it by 1 million, and that turns out to be the megaflop rating that's required. I've noted here 100. It could easily be 200, 300, 400, or 500 megaflops. So we've got the vertexes transformed. We're ready to convert them into pixels. That's the process of rasterization. The easy part of that is selecting which pixels in the frame buffer are indeed occluded by that primitive. It can be significantly more work to determine what values those pixels should be assigned, in particular what red, green, and blue intensity should be assigned to those pixels. The kind of options that come up here, we might choose to do something called smooth shading, where instead of just assigning the color to all the pixels that came with one of the vertexes, say of a line, we interpolate color values between the values at the two vertexes that define the endpoints of the line. There's a significant amount of arithmetic to doing that, but not nearly as much as what you have to do if you choose to try to select pixels not just with a binary decision tree saying either the pixel is in the line or isn't. We could say instead how much of the pixel is covered by the line. If we do that, there is significantly more calculation again. In the end, if we're drawing something fairly straightforward like a point without doing careful sampling and obviously without doing any interpolation, rasterization doesn't add up to much work at all. If, on the other hand, we're drawing a triangle and we are attempting to sample pixels properly and we are interpolating color values over it, and perhaps we're actually doing a lookup and mapping an image onto that triangle and compensating for the effects of atmosphere between the viewer and the triangle and the scene, it turns out that the amount of arithmetic that can be required can actually be greater than the arithmetic that we put into the effort of transforming the vertexes in the first place. So here we're looking at another some number of hundreds of megaflops. Finally, when we've got the pixels in hand, we need to move to write those pixels into a frame buffer. The frame buffer, remember, 1280 by 1024 pixels works out to about 1.3 million pixels in the frame buffer. We're rendering at 60 frames per second, and we're rendering each pixel more than once. I've suggested 4 times here, for example. That works out to about 300 million writes per second, which in and of itself is a pretty substantial number. But you might ask, why is it that pixels are written more than once? The answer is that typically in an interestingly complex scene, each pixel is covered by more than one object in that scene. So objects will render to more than one pixel. And since we haven't done that work ahead of time, we'll do that work in the frame buffer. The key notion here is we're not going to just render an image into this frame buffer. What we're doing is computing an image in the frame buffer. The most straightforward kind of computation to do there is called z-buffering. Z-buffering means in addition to storing at each pixel location in the frame buffer a red, green, and blue intensity, we also store the distance that that pixel was from the viewer. Now when another pixel is rasterized and arrives at that pixel location, we compare the distance it was from the viewer with the distance of the pixel that's already there. And whichever one's closer wins. The result of that is we've distributed the problem of solving the hidden surface elimination, making sure that what's visible in the frame buffer is just what should be seen. We've distributed that problem from being back on the host computer, where it's a very complicated problem, to being solved in the frame buffer, where it's a very, very simple problem to solve, but at the cost of doing a fair amount of arithmetic. So again, supposing it's 4 writes, and each one of those writes involves modifying a z-value, now we're up to 8 effective writes, or 600 million operations per pixel. Now, consider if we had been doing careful anti-aliasing calculations so that the values that are arriving in the frame buffer, the pixels that are arriving, aren't intended to just replace pixels that are already there, but instead are to be blended with them, with a ratio depending on what fraction of the new pixel actually was covered by the primitive being rasterized. If we're doing that, that can add an order of magnitude to the computation again. So in the end of all this, what we find is that we're doing billions of operations per second in order to do an adequate job of generating the final image in the frame buffer. So the upshot of all this is that there is a dramatic amount of computation that has to be done. If we're going to render high quality, high performance scenes, we're looking at somewhere between 1/4 and 1/2 billion floating point operations per second and several billion integer operations to merge the pixels into the frame buffer. Of course, we could do a lower quality or a lower performance scene, and given today's processor capabilities, do the per vertex calculations and perhaps some of the rasterization calculations with a general purpose processor. But any reasonable implementation that's going to try to keep up with those billions of pixel operations per second is going to have some hardware acceleration to do it. For the purpose of this discussion, we're going to work on the model that we're doing a good job and that we're going to use hardware acceleration to do all of these calculations, the per vertex, the rasterization, and the per pixel. Okay, so now we've reached the main subject of the talk, the actual design trade-offs for hardware graphics accelerators. We've seen that the computational requirements for doing interactive 3D graphics are very high. As a result, because these computation requirements are so high, the interesting systems that we consider, the architectures of those systems, will be implemented using one or more forms of parallelism. Some things to keep in mind as we review the design options are the following. First, the order of operations that are done matters in all cases. It matters particularly when the 3D graphics system is being used to do 2D graphics, such as rendering using the X rendering system or the Windows GDI system. It also matters, however, even in the case of doing 3D graphics. So while a z-buffer would appear to resolve the order requirements and it would be possible to render without concern of order, typically there are tricks done in rendering that don't have that property. It's not a good idea to give up on the sequencing of the operations. So the order matters. Second, efficient use of parallel systems, any parallel system, graphics or otherwise, requires that the computational load be nearly balanced between the various computing elements. And finally, programmability and adaptability of the resulting parallel system are influenced by its parallel organization. Of course, this influence is always going to be negative. The trick is to find out how we can minimize that influence to come up with the most programmable and most adaptable system. All right, so first let's consider the per vertex part of the architecture. There are 3 kinds of parallelism we'll consider. The first is pipeline parallelism. The second, SIMD parallel, in which case there's a single sequencer driving multiple data paths. And the third, MIMD parallel, where each of the multiple data paths is driven by its own sequencer. In the following slides, I'll put up a simple diagram to describe each of these and then comment about the advantages and disadvantages of each. In each of the slides that has a block diagram, the blue block represents a sequencer and the red block represents a data path. So first, the pipeline organization. In a pipeline vertex processor, vertexes are passed from one processor to the next. Each processor executes a specific portion of the per vertex algorithm. For example, in a 4-processor pipeline, we might have the first processor transform the vertex position and transform the vertex normal. The second processor do the lighting calculations. The third processor handle clipping. and the fourth, project the resulting vertexes to the screen. The advantages of a system like this are, first, that obviously it matches the semantics of the problem. We describe the operations to a vertex as being a sequence of things, and obviously that sequence maps directly onto this architecture. Also, this architecture minimizes the amount of code that's required for each of the processors. Since each processor is implementing only a fraction of the algorithm, it needs code space only to store a fraction of the algorithm. It's also clear that this organization maintains the order of the operations in a fairly obvious and simple way. Things can't get out of order. There's no passing lane here. There's nothing in parallel. Everything is stacked in sequence. A system like this is fairly easy to design, and it turns out it's easy to code. Again, for a similar kind of reason, because there isn't any passing or problems with things getting out of sequence or being done out of order. The code is straightforward. So what are the problems with an organization like this? Well, one is obvious that the data, all of the vertex data, have to be moved every time from each processor to the next. So the more processors we add, the more times all of the data, either the original data that was provided or the intermediate computed data results, have to be passed completely from one processor to the next. That involves a lot of bandwidth, and it also, unless the designer is very, very careful, uses up some of the execution time that would otherwise be available. In particular, if the individual processes along here are themselves pipelined, it takes some startup time to get them going with a new batch of data, and there's some shutdown cost when they're finishing up. A second problem is it's very difficult, nearly impossible, to balance the load on the processors in a pipeline architecture. For example, if the third processor actually does need to clip a vertex as opposed to just testing to see if it needs clipping, it can easily take 10 times the amount of execution time it would take otherwise. And what we end up with in a case like that is a weak link in a chain. The other three processors are running at their normal speed. The third one's taking 10 times as long. Likewise, if the programmer selects a more complicated lighting algorithm, it's possible that the second processor takes 3 times as long as the other processors. In any event, it's difficult to migrate these algorithms around. We would lose the advantage of having the code space reduced, and we just basically lose the simplicity of the system if we try to migrate the operations up and down the pipeline. And finally, for similar reasons, it's not possible to do what's called culling optimization in architecture like this. An example of culling is to test and see if a vertex is visible or not before you go ahead and commit to doing a very expensive lighting calculation. Since the order of the operations in this pipeline is fixed, it's not possible to reach ahead and determine whether or not a vertex needs to be lighted before you come in and do that whole operation. All right, the second organization we'll talk about for vertex transformation is a SIMD organization. In the SIMD parallel configuration, each data path typically handles a single vertex, and all data paths are controlled by a single sequencer, again seen here in blue. The advantages of a SIMD system. One, load balancing is not affected by the rendering algorithm. So here the depth of the system is a depth of 1. If a programmer selects a more complicated lighting model, that same model will be applied to all the vertexes, and all of the data paths will be working with full efficiency on that, unlike in the pipeline system where only one of the data paths would have been burdened with the job of doing that more complicated lighting. Second advantage is it minimizes the amount of sequencer logic. Obviously, if it costs money to make sequencers, it's desirable from an expense standpoint to make 1 rather than making n, where in this example n would be 4. And finally, because the system operates basically in a lockstep manner, while you can imagine vertexes getting out of order, as a practical matter in a system like in a SIMD organization, the vertexes all step into the sequencer in one operation and then are clicked out in a subsequent operation, and there's no problem with things getting out of order. So what's not so good about the SIMD organization? Well, first, it's difficult to deal with the modality in these algorithms. What I mean by that, for example, the relationship of the vertexes in the space they're defined in and the to the eye is represented by a matrix, and that matrix will need to be broadcast to all of the data paths in the system, and all the data paths will have to completely operate on it. So whereas we could broadcast vertexes, our primary concern, to just one of the data paths, we're forced to broadcast some other information to all of them, and the resulting loss of efficiency. It gets worse than that, though, if there are kinds of data, for example, the color of vertexes, that we would really like to not have to broadcast to all of them, because it's frequently the case that people provide a color with each vertex. But on the other hand, the programmer might not provide color with vertexes, and in that case, the color of the previous vertex has to be used for the one that's just come in. And dealing with that kind of smearing of state information is complicated. That complexity shows up with the SIMD parallel. We'll see it again in the MIMD parallel organization. Another problem with the SIMD organization is that any kind of branching in the code results in inefficiency. We saw that a programmatic change in the algorithm had no negative impact on the efficiency, but a data-related change in the algorithm, for example, one of the vertexes needs to be clipped because it's outside the viewing volume and the other three aren't, that does have an effect on the efficiency because the machine can be doing only one thing at a time. So in the worst case, all of the vertexes would be out, but they would be out in different ways, and the SIMD machine would have to handle each of those vertexes in order. And so at all times, 3 of the 4 data paths would be doing nothing. Finally, largely for that reason, it's more difficult to code the SIMD organization than it is to code the pipeline machine. As a practical matter, what you get with the SIMD machine is something that is probably a pretty good benchmark machine, but it doesn't do a real good job of handling dynamic data sets. So it produces high numbers for exactly what it's designed to do, but as soon as anything comes along that's out of the ordinary, the different processors are forced to be sequentialized rather than operating in parallel, and the performance goes way down. So finally, let's consider the multiple instruction, multiple data parallel organization. In the MIMD organization, each processor handles either a single vertex or perhaps all of the vertexes related to a single primitive. Each processor consists of both a data path and an independent sequencer. So what's good about this organization? Well, obviously, it's easy to program. From the standpoint of someone programming this system, it's no different whether there's 1 processor or 10. So it's as easy to program as if there were just 1 processor. For similar kind of reasons, it's very modular. It's possible with a MIMD organization to take out or to add processors to the extent that the hardware, the sockets and connectors in the system will allow it. It's easy to deal with adding and subtracting processors. Again, the programming really doesn't handle it. The programming exists in its entirety on each one of these processors. Another thing is that both static and dynamic load balancing are possible. By static load balancing, what I mean is, although the execution time for the algorithm may vary from in either vertex or primitive to primitive, we can put a FIFO at the front and the back of each one of these processors, and over time that'll all average out. By dynamic, I mean instead of just adding FIFOs to the system, actually measuring which of the processors is most busy and which is least, and adding new work units to the one that has the least workload already accumulated. Another advantage of the MIMD system is that the processors can be implemented using standard off-the-shelf microprocessors. You can't buy an off-the-shelf data path, but you can go out and buy a microprocessor that has its own sequencer and data path in it. Another advantage is the call optimization we talked about not being possible in a pipeline system is not only possible but trivially implemented in the MIMD parallel system. Since there are multiple sequencers, the different data paths can be operating independently, and it's very easy to write your programming so that it looks ahead to determine whether vertexes are indeed visible before it commits to doing a whole lot of complicated work on those vertexes. And finally, for those of you who are familiar with parallel architectures, you'll recognize that MIMD is a fairly standard architecture for general purpose parallel machines as well. The thing that distinguishes this graphics MIMD implementation from a more general purpose implementation is the graphics implementation really doesn't have to deal with interprocessor communication at all. So whereas if you're designing a general purpose multiprocessor system, probably, almost certainly, your largest concern is passing data between the processors, and in the common case that the data are cached at each processor, making sure that the caches have coherent data. In the graphics implementation, there is no data being passed, so it's a far simpler implementation than a general purpose MIMD. So given that, what are the problems with a MIMD organization? Well, the first obvious thing is it's kind of got the most of everything, so it's likely to be more expensive than the other implementations. Also, the operational sequence, the order that things come out, is not trivially related to the order that things go in. In particular, if you take advantage of large FIFOs or doing dynamic load balancing and sending work units to the processor that's most available, you've got to pay a lot of attention to how you take those work units back out the other side of the MIMD system. The FIFOs that we talked about for achieving the load balance are themselves not inexpensive, and they may have to be fairly large. For example, the amount of FIFO depth that's required to actually smooth out all of the flow is n-1 times the ratio of the shortest execution period to the longest execution period. So for example, if it takes 3 times as long to clip a vertex as it takes to not clip it, and there are 8 processors in the system, then the FIFO has to have a depth of about 20 vertexes. And finally, just as it was in the SIMD organization, it's difficult to implement modal distribution of data. So what's actually happening in that big world of implemented architectures out there? For one thing, the algorithms that are being implemented are becoming more complex, whereas 5 or 10 years ago, it was acceptable to do just a very simple lighting model or perhaps no lighting model at all. It's now expected by people who use these machines that they will support multiple lighting sources. They will support calculations that take into account position and angle and distance of lights. And as a result, it's really impossible to do a good job of balancing the execution of the per vertex operations on a pipeline system. A second thing that's happened is that today there are a lot of microprocessors out there that are available with cache memory on the microprocessor. So what that means is, whereas in the past, if you wanted to build a MIMD system and you wanted it to run fast, you probably had to buy static RAM memory for each of the processors. Today, since a small amount of static RAM is included in the processors as you buy them, you can implement the memory with dynamic RAM, which is dramatically less expensive. So the cost differential of going to a MIMD system has gone down substantially. And as a result, what we're seeing is machines today more and more commonly have MIMD organizations, and essentially never are pipeline organizations. In some cases, they do use SIMD parallelism. Okay, so for now, we'll skip the issue of the kind of hardware that's used for the rasterization part of the process and move directly on to the hardware used for the per pixel operations. Here again, we would consider the same 3 types of parallelism. It turns out, however, that pipeline parallelism isn't a viable option in a high-end machine for several reasons, the most straightforward of which is just that the greatest bottleneck in this, remember we're talking hundreds of millions or billions of writes per second, is the bandwidth into the memory. There's no way that a parallel organization that ends with a single spigot at the bottom is going to be able to fill memory at the kind of rates we require. So it makes sense that the organizations we'll look at are organizations that are highly parallel so that we can get the advantage of the increased memory bandwidth that results. Pipeline does make sense for a low-end machine where you're not trying to do better than the amount of bandwidth that's available with a simple memory system. It turns out it also makes sense as the implementation technique for the individual data paths in either a SIMD or a MIMD pixel parallel system. And what you notice from looking at that is that parallelism in high-end machines has a kind of fractal-like quality. It's not fractal exactly because it doesn't go on indefinitely, but it is the case that as you look more closely at a high-end machine, you tend to see another level of parallelism. For the purpose of this talk, what I've been dealing with is just the highest level of parallelism that's available, but you should keep in mind that parallelism exists at several different levels in these machines. In all of these diagrams, blue will continue to be used for the sequencer, red for the data path, and green will represent memory. Before we talk about whether we use SIMD or MIMD parallelism in the pixel area, we have to talk about the general partitioning of the frame buffer, how the memory of the frame buffer is mapped to the processors of the frame buffer, whether they have a single sequencer or separate sequencers. There's basically 2 obvious ways to go here. One is to just break the screen up into large coarse tiles and assign one processor to each one of these tiles. A problem with this, it's typically done in systems where there are fewer processors than there are tiles. As a result, in order to render a scene completely, all of the primitives that describe the scene have to be passed through the system multiple times, either by the application program or more typically by being accumulated somewhere in the graphics system and then passed through multiple times. Straightforward thing to do, but it has a very bad effect on context switching, which we haven't gotten to yet, but you can imagine that just dealing with that bulk of data, all of the primitives that describe a scene as part of the context of the machine, is a significant problem. So this discussion, we're not going to talk about coarse grain tiling anymore. Fine grain tiling, in this case, what happens is the screen is broken up into small tiles, and each of those small tiles has 1 pixel assigned to each of the processors in the system. So the example that you're looking at, the 1 small tile in the lower left, has all 20 processors, in this example, mapped to it. The advantage of that is it basically trivially takes care of a load balancing problem. Except for very, very small primitives, a primitive is likely to hit most or all of the processors that deal with pixels. And it requires no complicated queuing of primitives in order to accomplish this. So this is the kind of parallelism we will concentrate on in the next few pages. The limiting case for these 2 kinds of parallelism is exactly the same thing, 1 processor per pixel. It is a limiting case. We haven't reached it yet. So first we'll consider the single instruction multiple data implementation. In the SIMD tile configuration, each data path is connected directly to a fraction of the frame buffer memory. That's how we get the bandwidth here. And all of the data paths are controlled by a single sequencer. So what are the advantages of the SIMD organization? Well, first, obviously, just like the SIMD organization for per vertex calculations, it minimizes the cost of the sequencer. There's only one of them. A second advantage is that, at least in the simplifying case where all of the processors are operating on pixels from the same primitive, it simplifies the flow of control. There don't need to be large FIFOs. Everything is happening, again, in lockstep. What are the problems? Well, it may very well turn out that the cost of distributing the control from the one sequencer to all of the data paths is greater than the cost of just providing a separate sequencer for each data path. This happens for a couple reasons. One is that the algorithms that are being implemented at the per pixel level are very simple, so the cost of a sequencer is very low. And the other problem is we would like, just as we talked about being able to do expansion, have expandability in our parallel systems for vertexes, it's nice with pixels as well. And it may well be that that expansion goes from one board to another. And again, if it goes from one board to another, the cost of distributing the communication can be substantial. A second problem is these systems don't scale well. It isn't the case in the simplifying case again, where all of the processors are operating on the same primitive, pixels from the same primitive. The scaling is very poor. It turns out that primitives aren't that large, and even primitives that are large don't tend to have a very good aspect ratio. What I mean by aspect ratio is instead of a pixel, a polygon with 100 pixels being a 10 by 10, it's more likely to be a 2 by 50. Right? So in that case, it will probably not hit all the processors, in particular if all the processors is a large number. So people have done some calculations on that we won't go over here, but basically it's pretty easy to get less than 50% efficiency with something like a 4 by 4 tile, and once you get up to an 8 by 8 or 10 by 10 tile, you're getting very, very poor utilization of those processors. The effect that is that poor utilization is one I call a cookie cutter, because I imagine stamping out the processors onto the image instead of distributing pixels as they're generated onto the processors. Okay, so let's consider now the MIMD tile organization. In the MIMD organization, each data path is again connected directly to a fraction of the frame buffer memory. However, each data path has its own independent sequencer. So what are the advantages of this organization? One thing is it easily supports more complicated algorithms. So simple pixel algorithms probably don't have any branches in them, and they would be implemented efficiently in the SIMD system. But complicated algorithms may well have branches in them, and those algorithms will be supported much more efficiently on a MIMD system. Second, as we talked about before, the MIMD organization minimizes wiring. All we have to do for wiring now is to somehow broadcast the information about which pixels are to be rendered. We don't have to deal with broadcasting all the instructions for how to merge them into the frame buffer as well. Third advantage is that a culling optimization is possible, just like it was true with the vertexes. If you're implementing a complicated pixel algorithm, it's possible to cut to the chase and decide, well, gee, that pixel isn't visible because it's farther away than the one that's in the frame buffer already, so I'm not going to take the time to do all the other calculations that I would have done. That kind of optimization is possible here. It would not be possible in SIMD. And again, just as was the case with the parallel system before, interprocessor communication is not required. So the MIMD does not have what you would expect to be the high cost of communication between all these processors. The processors operate independently. So what's the problem with a MIMD organization? Well, again, just as before, it's likely to be more expensive, although we've seen that may not be true. And again, in order to achieve reasonable efficiency, you have to build large FIFOs at the front of each one of these things. If you don't build the FIFOs in, you get the same cookie cutter problem you got with the SIMD. It's just it's difficult to put the FIFOs in the SIMD implementation. It's straightforward in the MIMD implementation. What that means is that if you want to build a large tile, if you wanted to build a system with, say, with an 8 by 10 tile, 80 processors, you would have to go ahead and add the expense of the FIFOs at each one, but at least with the MIMD organization, you could do that. Something that's important to keep in mind is that unlike the previous MIMD example, the operation sequencing is not a problem here. Yes, it's true if you organize a MIMD frame buffer and give each pixel processor a FIFO that they may indeed be operating on the pixels out of order, but it doesn't matter. There's no reconnection of these data paths. This is the end of the line in the frame buffer. So it's insignificant from a programmatic standpoint whether one of the pixel processors operates on all of its pixels before the second one even starts. So we've completed talking about the per vertex and the per pixel part of the operation. I'm going to go back now and speak just for a moment about the rasterization. Basically, there's two options here. One is to take as much advantage as possible of the hardware we've already talked about for doing per vertex calculations and per pixel calculations. The other is to add some significant amount of hardware to do the rasterization. In that case, that hardware can be broken up into two sections. One is basically doing setup, typically floating point operations that compute what the edge slopes are, what the slopes of the color values are if we're going to interpolate colors, what the slopes of the texture coordinates are if we're going to map an image onto the primitive, etc. It's all information to get ready for doing the actual pixel generation, which is the second part of the process, using those pre-computed values, interpolating them typically to generate the actual pixels and their associated data. So let's consider a couple of complete machine architectures and see how these things all play together. The first is an architecture that is completely a SIMD architecture. It's reminiscent of the Silicon Graphics VGX architecture that shipped a couple of years ago. In this case, looking at the diagram, vertexes are entering at the top of the diagram. Note that the SIMD per vertex parallelism forces the addition of hardware to distribute vertexes to the data path. So that's that box at the top called distribute vertexes. Something's got to make a decision about which vertexes go where, and that same box is going to handle the issue of smearing mode across, broadcasting matrices, making sure that the right color shows up with the right vertex at each of these data paths. So that's one additional expense of this kind of parallelism. Then we also notice that in between the per vertex SIMD section and the per primitive SIMD section, which is doing the rasterization setup, we also require another box. And this box reorganizes the vertexes that have been transformed in the per vertex section into primitives. So for example, if a quadrilateral shows up at this system, its 4 vertexes would be distributed to the 4 vertex processors on top. Then all 4 of those vertexes would be passed to one of the per primitive processors in the next SIMD level. That reorganizer is also a significant expense in this system. And then finally, the SIMD frame buffer at the bottom is likely to suffer from the cookie cutter inefficiency that we talked about before. We're not anticipating a great deal of FIFOing in the system. There's just the one sequencer. So probably that sequencer will be operating on just one primitive at a time. Another example, consider a system that's almost entirely MIMD organized. Here it's possible to completely eliminate hardware dedicated only to the per primitive portion of rasterization. Instead, the per primitive rasterization calculations can be done on the per vertex hardware. And that's because instead of sending just individual vertexes to this per vertex MIMD hardware, we're going to send all the vertexes for each primitive to one of the processors. So for example, if 4 triangles had shown up, each of the triangles would be implemented on one of the 4 processors, and each processor would first do the per vertex algorithm on all 3 of those vertexes, and then go on to do the per primitive rasterization setups. In principle, the per pixel portion of rasterization could be done in the pixel data paths. But it's a lot more efficient to implement a separate per pixel rasterization layer that you see there in between the MIMD per vertex per primitive stuff and the per pixel MIMD at the bottom. It's particularly true that this is more efficient if what's going on is that you are indeed mapping images onto your polygons. In that case, you need a complete copy of the image at every one of these paths. You would need 20 copies if you stored the images at the per pixel processors. You need only 5 copies if you store the images at these introduced per pixel rasterization processors. So you see that in both of these cases, we ended up with some amount of processing per primitive. In the first, the per primitive stuff was a setup, and we were doing the per pixel part of rasterization in the SIMD back end. In the MIMD organization, it was possible to do the per primitive part of the rasterization on the per vertex MIMD part of the system because, again, the vertexes were distributed in sets of complete primitives, but in that case it wasn't possible to do the per pixel part of the rasterization on the per pixel processors, and instead we added a separate level for that. Okay, I promised earlier that I'd spend a little time talking about the problems of context switching in these architectures. In a workstation or personal computer environment, it's important that the graphics system not only render primitives quickly, but also switch quickly from rendering in one window to rendering in another. Many architectural decisions that favor fast rendering work against fast context switching. For example, we've seen that as we add more and more processors, we get faster and faster rendering, but as we add more processors, we greatly complicate the task of extracting the context from each processor, storing it somewhere, and loading in an alternate context. So the more processors works in favor of rendering performance, but it works against the performance of context switching. Likewise, those large FIFOs that we put in there to make the load balance very nicely are also a huge amount of state that also have to be read out, swapped somewhere, and loaded back in when the context changes. If there are large context switch latencies, they affect the efficiency of the operating system. Obviously, just like the amount of time it takes to load and store the registers in the processor makes a difference for the operating system, a bulky context switch like the amount of data required to operate on one of these parallel systems can have a huge effect on the efficiency of the operating system. So it's important that the context switch time be minimized, and if it can't be eliminated, it's useful to arrange the system so that the switch happens itself in parallel with the processor doing whatever it does. So if you first work to make the context switch as fast as possible, and then make sure that the implementation allows the switch to take place largely in parallel with the operation of the general purpose processor. If the switch takes a really long time, for example, if you allow the system to operate on very, very hard to execute primitives, say a polygon that fills the whole screen, and you fill up a FIFO with a bunch of polygons that fill the whole screen, and you don't implement your context switching in such a way that it can flush those things without executing them, you can actually get latencies that are great enough to affect the usability of the system. Somebody moves the cursor, tries typing in another window, and nothing happens for a few seconds. So the context switching at fine grain is important to the operating system, and if it's not watched out for carefully, it can even affect the usability of the system. The thing to note here is that most of the literature regarding high-performance graphics ignores the issue of context switching. People like to write papers about how to make systems draw fast. People don't like to write papers about how to deal with the fact that they not only have to draw fast, but they also have to be able to draw lots of different things fast. I also promised we'd take a moment and talk about different architectures. We've considered only architectures that physically separate the per-vertex processors from the per-pixel processors. Right? We've looked at different ways to move the rasterization around, but all the architectures we've talked about have got stuff that deals with vertexes and other processors that deal with pixels. One obvious alternative is just say, no, what we'll do is we'll make a parallel array of processors and we'll let them have at it. What's the problem with this? Well, basically, what happens is all those nice things I said about communication, the fact that the processors don't have to deal with each other, goes away, because there is no clear relationship between the primitives and the pixels. You can't say a priori, these primitives will generate pixels that go to these processors, and these will generate pixels that go there. So if you distribute the primitives around the system and then redistribute all the pixels, you end up with a huge communication bottleneck. In any event, if you're going to do something as complicated as that, you might as well just build yourself a general purpose computer, or better yet, buy one from somebody else. Another possibility is to assign a single processor to each primitive in the scene. This is a technique that's commonly used in image generators for flight simulation systems, but you won't find it in workstations. Basically, the reason is that it means that all of the primitives have to be loaded into the hardware in order to execute the rendering. There's two problems with that. One is there's obviously a finite limit on how many primitives there can be, and that's a problem. People don't like to have a finite limit on the complexity of their scenes. And second, you've got, again, a huge amount of context. If we've loaded all of the primitives that describe the whole scene into the hardware, and then we change our mind and decide to render something else, it's a big job to swap that stuff in and out. So finally, let's look back and extract some important design guidelines from the material that we've covered. First, it's not worth doing a special purpose machine if it doesn't have a special purpose. Recall that we carefully described a simple processing model for three-dimensional graphics before we considered special purpose architectures. It's important as the design progresses to stay focused. Don't end up solving a general purpose problem with a special purpose machine. Given that, however, it remains true that the best special purpose machine is the simplest one that will do the job. A Rube Goldberg contraption that precisely matches a specific task is never the right answer. What we're looking for is a balance of focus and generality that results in a simple, efficient machine. I like to think of focus as selecting an area for design optimization. Possibilities outside that area are ignored, but within the area, every attempt is made to be as general as possible. The notion of orthogonality, that independence is better than dependence, can be helpful in generalizing the focus area. Look for underlying elements in the system that are common to each element, but independent of each other. For example, we found that points, lines, and polygons are all represented by vertexes, and all are reduced to pixels. By operating on vertexes and pixels rather than on primitives, we succeed in making much of the treatment of primitive independent of primitive type. This is both better for the implementer and for the programmer. It's better for the implementer because it really focuses what the hardware is doing. We've got a section that deals with vertexes, and it doesn't care where the vertexes came from. We've got another section of the hardware that deals with pixels, and again, that section doesn't care what kind of primitive generated the pixels. It's better for the programmer because it makes the instruction set more RISC-like. And for the same reasons, it's possible to know. If you know that lighting calculations work for polygons, you know they work for lines and points because you know the system doesn't treat them differently since the system just treats them all as vertexes. The seemingly incompatible goals of focus and generality are nicely balanced in a good design. So finally, what have we seen? We've seen that billions of operations per second are required to do high-quality graphics. We've seen that graphics computations are easily parallelized. As a result of those two things, we understand it makes sense, it's necessary, and it's possible to build special-purpose hardware that does a good job of rendering high-performance interactive graphics. We've also seen that the Framebuffer is an active participant in image generation. It isn't just the place that the image is placed after it's been computed. It is, in fact, the place where the computation happens. And we're seeing a trend in the industry that this is true more and more. And finally, we've seen that well-designed machines have a nice balance of focus and generality, emphasizing simplicity and orthogonality. So as I mentioned at the start of this talk, I've been doing this work for about 10 years. If I'd given this talk 5 years ago, it would have been fairly different than the way I gave it today. And I expect if I give it again 5 years from now, it will be different then too. I look forward to doing that, and I look forward to working with some of you in the interim. Thanks for listening.